Hello everyone, my name is Spaniol. I'm a master student at Université Paris-Saclay at ISMO under the direction of Marie-Aline Martin and Olivier Pirali. And today I will talk about the technical enhancement of submillimeter-wave spectrometer and the laboratory detection of new lines of methanol radical derivatives. So many molecules in space are radicals. So they have a major importance for astrochemistry. The question is, why should we investigate the rotational spectrum of methanol radical derivative? It's because it contains carbon, oxygen, and hydrogen. CH2OH, one of the radicals, is potentially a precursor of complex organic molecules, and CH3O is already detected in the interstellar medium. At ISMO, we have two spectrometers and we have different cells for what we want to do. If we want to scan stable molecule or radicals. Today, I will just present the frequency multiplication-based millimeter wave spectrometer and the H abstraction with the flow cell. We used the fluorine H abstraction to produce the radicals. In the methanol, we have two hydrogen that we can remove. The problem is that we produce just a little bit of radicals. They have a high reactivity and a short lifetime, so we have a low signal-to-noise ratio. And sometimes they can be hidden in the precursor lines. So we need to improve our sensitivity. We need to improve the absorption through the Beer-Lambert law. And we need to improve our discrimination power to know if the line is hidden or not in the precursor line. CH2OH and CH3O have been already scanned by our team in a published paper. We used a synthesizer to produce the light, 2 to 20 gigahertz, with a frequency multiplier from VDI. We have a detector, Schottky or bolometer, and we use the frequency modulation plus a second harmonic detection to detect the line of the radicals. We have a 150 centimeter cell, and we produce the radical by fluorine H abstraction, and the fluorine atomite, and the atomite fluorine is produced by a microwave discharge. A typical spectra is recorded in 1 minute and 40 seconds for a 10 megahertz span, and we have a root plus primary vacuum pump here. So with this initial setup, we try to record a line of CH3O around 191. When we scan this area, we have 3 lines. So how to know which lines is from the radicals and which is from the precursor? We use the effect of the magnetic field on an open shell species called the Zeeman interaction. This interaction between the energy levels of radicals and the magnetic field will split the energy levels. So the absorption will decrease in a single point. So we draw 2 spectra, one in black without magnet, and one with magnet in red, with a permanent magnet under the cell. We see that 2 lines doesn't change between the 2 spectra, and one decrease. That means this line is an open shell species, and we assume that it's CH3O. So after, we try to record the line of CH2OH, predict here. But when we record the spectra, we see 2 lines on each side of the prediction. And when we see on splatterlog, we saw that it's CH3OH lines. So we try to record the spectra with the magnet to see if, thanks to the Zeeman interaction, we can see the line of the radicals. And when we made the comparison, it's clearly here. No, maybe you will see better if I made the difference of the spectrum. So we have a light, but it's very noisy. And we discovered something interesting. When we move the permanent magnet away, the signal of CH2H disappears completely. It means that we have a very short area of radical production. So the first enhancement that we made is to triple the area of radical production and to shorten the injection tube from 1 meter and 25 centimeter to 40 centimeter. So we decrease the recombination of atomic fluorine and we increase the synthesis yield of radicals by multiplying the area by 3. Then we decided to make a double pass. So we still have our source. The light goes through a polarizing grid. Since the light is 0 degree polarization, has a 0 degree polarization. Then at the end of the cell, we put a rooftop mirror to send back the light with a 90 degree polarization. On the polarizing grid, it reflects to an off-axis parabolic mirror, and we detect the light here. So we artificially double the length of the cells. And then we have a problem with the permanent magnet because we have to record 2 spectra for each line. And sometimes if we forget to remove the magnetic field, when we record, we don't see lines, but we don't know why, because we forget to remove the permanent magnet. So we decide to improve the discrimination power and to make it easier to do. We hold 800 coils all along the cells. And with an alternative current of 2 amperes, we produced by an audio amplifier and a diode, we produce a 16 Gauss magnetic field. Then we modulate the magnetic field during the spectra. We have a larger magnetic field than previously with only the permanent magnet, so we have a larger Zeeman splitting. Then, with the second lock-in, we demodulate the signal at the frequency of the magnetic field modulation. We have 2 outputs. The first on the first lock-in, it's the single demodulation with the frequency modulation, as before. But on the second lock-in, we have a dual demodulation with so the frequency one and the magnetic field one, and this is the result. It's only the result of the lines which has changed during the magnetic field off and on. So before, we have an initial setup with one area of production, a single pass and single modulation, and the final setup with a triple area of production, a double pass and a double modulation, frequency one and magnetic field one. Before, we need to record 2 spectra for each lines for a total of 3 minutes and 12 seconds. And now we only record 1 spectra for each lines, 3 minutes and 25 seconds. But we don't have to put the magnet or to remove the magnet. Before, we have around a signal to noise ratio of 2 on the weakest lines, and now it's more like 10. It's 5 times better for the same condition and for the same time of acquisition. And with this setup, we succeed to record around 500 of new lines of CH2H and 500 new lines of CH3O, up to 900 GHz. If you want to know more about this new record, you can see the Olivia Chitara's talk. And now, with this setup, we decide to study other interesting radicals, CH2CN, from other precursors. In the future, we want to apply a larger current to have a larger magnetic fields and so to have a better modulation. And the final step would be to have a Fabry-Perot cavity to increase the length artificially by several orders of magnitude, so to increase the absorption by several orders of magnitude. I would like to thank all my collaborators and all the funding agencies.